In this video, we present our ICCV 23 paper, TextPSG, Panoptic Scene Graph Generation from Textual Descriptions. A scene graph is a directed graph-based abstract representation of the objects and their relations within a scene. Typically, in a scene graph, each node denotes an object located by a bounding box with a semantic label, and each directed edge denotes the relation between a pair of objects with a predicate label. A recent work proposes the concept of panoptic scene graph, in which each object is grounded by a panoptic segmentation mask instead of a bounding box, for a more comprehensive structured representation. However, all existing works approach panoptic scene graph generation by learning segmentation and relation prediction from manually annotated datasets. Unfortunately, it is extremely labor-intensive to build such datasets, making it difficult to scale up to cover more complex scenes, thus significantly limiting the generalizability and the application to the real world. Inspired by previous weakly supervised methods, in this paper, we introduce a new problem, panoptic scene graph generation from purely textual descriptions, to explore a holistic structured scene understanding without labor-intensive data annotation. The word purely here denotes three constraints we set, which results in a very challenging problem. First, only image caption pairs are provided during training, without any location priors in either pre-trained region proposal networks or location supervision. Second, the explicit links between regions in images and entities in captions are not provided. Third, no concept sets are predefined, which means the target object semantic and relation predicate concepts defined for inference are unknown during training. Given these constraints, we argue that there are two key challenges to learn a structured understanding from image caption pairs. First, the model should learn to partition the scene and ground entities in language onto the visual scene. Second, the model should also learn the object semantics and the relation predicates purely from textual descriptions. By solving these challenges, the model could associate visual scene patterns with textual descriptions, gradually acquire common sense among them, and finally reach a more comprehensive and generalizable understanding. We propose a novel modularized framework, TextPSG, as the first step towards this problem. During training, TextPSG takes batched image caption pairs as input. For each pair, the image is passed through the region grouper to be partitioned into several image segments, while the caption is first preprocessed and then taken by the entity grounder to ground textual entities onto the image segments through a fine-grained contrastive learning strategy. With the grounding results as pseudo-labels, the segment merger learns similarity matrices between segments for inference time merging, while the label generator learns the prediction of object semantics and relation predicates. Specifically, in the segment merger, we propose to leverage the grounding as explicit supervision for merging to improve the ability of location. In the label generator, we propose to reformulate the label prediction as an autoregressive generation problem, and employ a pre-trained language model as the decoder to leverage the pre-learned common sense. We further design a novel prompt embedding-based technique to better incorporate the common sense. During inference, for each input image, the image segments output from the region grouper are directly passed to the segment merger to further merged, and then fed to the label generator to predict the labels. As shown in the red box, our framework significantly outperforms all the baselines under the same constraints. Our method also shows better performance than the baseline, which utilizes location priors by leveraging a pre-trained detector. Our framework is able to provide fine-grained semantic labels to each pixel in the image to reach a panoptic understanding, while the proposal-based baseline can only provide sparse boxes produced by the detector. Furthermore, our framework can generate comprehensive object semantics and relation predicates through the autoregressive generation, such as dry grass field and land at, showing the open vocabulary potential of our framework. Our framework shows strong out-of-distribution robustness. As shown in the table, the baselines suffer a significant performance drop from the in-distribution triplet set to the out-of-distribution triplet set. While our framework, with the ability of location learned from purely textual descriptions, can reach similar performance on both sets. As a side product, we demonstrate that our entity grounder and segment merger can also enhance the text-supervised semantic segmentation, reaching an absolute 2.15% improvement of MUU on COCO compared with the fine-tuned group IT. Please refer to our paper for more visualization, analysis, and discussion. Thank you for watching.